All right, we're moving on to section 2, so we're really going to start looking at limits from a graphically and numerical point of view. We talked a little about limits in section 1, just what numbers are approaching instead of what they actually equal, and so we're going to work on that. All right, so we are going to explore y equals x cubed minus 1 over x minus 1 at the value x equals 1. We're going to do it both graphically and numerically. You notice I cannot evaluate at x equals 1 because if I plug in 1, the denominator would be 0. Okay? If you have a denominator 0, it's undefined, therefore we don't have a value at it. So what we're going to do is look at what it looks like graphically, and we're going to look at what it looks like numerically. So if you have a graphing calculator, you go ahead and type something like that in your graphing calculator. Make sure you put the numerator and the denominator in parentheses whenever you put that in your calculator. I already did it on this calculator here, and you can see this graph here. Okay, so it looks almost like a parabola, except for the fact we know that at x is 1, if you were to go infinitely close to that, there's not a value. It does not exist at 1. All right, there's nothing here. Okay, so it doesn't matter, if I'm tracing along this line, at actually x equals 1, it's entirely undefined. So there's nothing there. Okay, so just keep that in mind. All right, so you kind of imagine like a hole here at x equals 1. If you notice it's just skipping over 1 every time. You can actually do a table of values if you want to do that, but it doesn't exist there. So there's a hole. So that's what it looks like there. So it looks U-shaped. It looks almost like a parabola, but it's missing exactly at 1. But what is it approaching? If you look, it appears that that y value is at 3. So that's one way to do it. You can kind of see what it's approaching. All right. You can't actually plug in 1, though. It's not actually equal to 3. It's just approaching 3. If we were looking at it numerically, I would consider a table of values. You could do the table of values before you graph it. You can do the graph before. It doesn't matter. But I would, start kind of far out, like -2, -1, 0, and then you're going to go as close to 1 as you can, but we're going to pick some values close to 1 but before 1 on the number line, and close to 1 but after 1 on the number line. So let's kind of picture 1 actually down here. Okay, so we could do, 0.75 or 3/4, and we could do 0.9, and we could do 0.999. We can take it pretty close. All right, and then we can get far away from it. So we could, or on the other side of it. So you go 0.01, so just barely past it. 1.1 kind of thing. 1.25, something like that. Okay, and then we can plug those values in and get those numbers. I'm going to try and pause this, and it's not going to work. Okay, so as we start plugging things in, we'll get, and you can use a calculator, 3, 1, 1, 2.3 approximately, rounding of course, 2.7, you can go on and on and on, 2.97. It's undefined here, right? This doesn't exist exactly. But we're trying to see what it's approaching as it gets close to 1. So as this gets really close to 1, those are arrows. What is it going to? So when I plug in numbers really close, this gives me 3.03. This gives me 3.3. This gives me 3.8, and so on. So if you look, this number, and you could plug in numbers even closer, 9999999 or 0.00001. It looks like it's approaching 3. And so from both of our evaluations that we looked at exploring based off the graph, numeric, so this introduced our limit. Our limit is what a value is approaching, not what it's equal to. So limit as x approaches 1 is actually, of y, is actually equal to 3. Now, if we were to plug in 1, it's undefined, but the limit is 3. It's what it's approaching. Okay, so we're going to evaluate the function at several different values near 0, just like we did, and then we'll use the results to estimate the limit. So we don't have to look at it graphically. We're just going to look at the table of values. So we are looking at it close to 0. So essentially, we're looking at the limit as x approaches 0 of x over root x plus 1 minus 1. Okay, and so let's plug in numbers close to 0. So if you go kind of far out, you could do, we'll put 0 in the middle. So we'll find values that are headed to 0 and figure out what value it's headed to other than being undefined. Because if I plug in 0, if you notice the denominator is also 0, which is undefined. All right, so let's plug in negative 0.003, negative 0.002, negative 0.001. So those are numbers on the number line to the left of 0. We can put some numbers to the right. So like 0.001, 0.002, 0.003. And there's fluidity in that. You don't have to choose those values. It just helps to pick values that are close. You could have done 0.1, 0.01, 0.001. It's whatever you want. And so I've already done this for us. This is 1.9985. If we were to take it far out, 1.999, 1.9995. This is undefined or does not exist here. And then I can plug in 0.001 and get 2.0005, 2.001, 2.0015. And if you notice, each time they're getting closer to what number? Well, this, if I were to round, would be approaching 2, and these would be rounding down, would be approaching 2 as well. So we can say this limit is approaching 2. Okay, we're going to find the limit, and this is a piecewise function that we have here, as x approaches 2. So we're looking at the limit of f of x as x approaches 2 of this whole function. All right, and I'm going to do it, I think it's easiest probably do it graphically. Okay, so if we graph it, so a review of piecewise functions, you're going to graph both functions, but they've given you domains. So these are your domains. And so it only exists for those certain x values. Okay, so if I'm graphing the line f of x equals 1, that is a horizontal line, y equals 1. And so it's here. The only thing it's not at 2. So I'm going to remember it doesn't exist at 2. So it is all of these y equals 1 values except at 2. And I'm putting an open circle there because there's a hole at 2 where it's not there based off that. And then at 2 would be the second part here. It's 0. And so it has a y value of 0 at 2. And so it looks like this. So we go, 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 and you're going to skip down to 0 and go, 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 go. Okay. But if we're looking at as it approaches, let me change colors here. This graph is approaching this y value from the left, and from the right, it's approaching this y value. It's not what it's equal to. F of 2 is 0. But the limit as x approaches 2 is actually 1. Because if you look, that y value is 1. So this limit is equal to 1. Okay, next example. So I'm adding in something that often trips us up, would be like an absolute value mixed in with other stuff, not by itself. So we know absolute value of x has like a V-shaped graph. It means, distance from 0, that old concept, but it's a little different when you mix it with other functions, like in this case, a quotient. And so in doing that, it does kind of change how it's going to work on what we're going to do. So the concept, though, of absolute value by itself is absolute value of x is a piecewise function. When the value of x is greater than or equal to 0, you get x, okay? And then when the value is less than 0, you're going to do the opposite sign of it, okay? Does that make sense? So if you're looking at this top part, if I plug in 0 up, I'm going to get the number itself. If I do this bottom one, I plug in, say, -1, I'm going to have to change its sign. So negative, -1. So that's where that comes in. So then if I evaluate this concept as it's given here, it's still a piecewise function, but then just divide it by exactly what it is. X divided by x is 1 when x is greater than or equal to 0. Negative x divided by x is -1 when x is less than 0. And so that's that graph. And if we look at that, or that's that concept, we look at that, that's a pretty easy piecewise 2 graph. When x is greater than, so this direction, okay, I get an output of 1, and it's equal to. So I get at 1, it's 1, and it continues to be 1 everywhere positive. But here, it's not equal to, so I use an open circle. To the left, it's -1. And so we have this piecewise function here. And so the question is, show that doesn't exist. In order for a limit to exist, it has to be approaching the same value from both sides. So if I look at what it's approaching from the right, it's approaching 1. From the left, it's approaching -1. So since 1 is not equal to -1, they're not approaching the same value, so the limit does not exist. And I'll just say D and E, where a limit does not exist. Okay. Now, we can do partial limits, and at some point you'll get to experience those as we go further in. Okay, another example is, sorry, I'm moving that around so much. Does the limit as x approaches 0 of 1 over x squared exist? Okay. You can, if you wanted to do, you could do the XY chart like we did previously. You could plug in numbers like really close to 0 if you wanted to and see what they're approaching. That's a fine way to do it. There's nothing wrong with that. You know, if I plug in -0.001 or -0.0001 or 0.0001 or -0.001, and you can do more values like that. You're going to be getting numbers. It's very interesting to see it as it happens, but they get big very, very, very fast. And so this would be something with a whole bunch of zeros. This would be something with a whole bunch of even more zeros. Hopefully those zeros are right. This, again, we're not sure exactly. We're trying to figure out what it's approaching, but it doesn't exist. You know, the output doesn't exist at that point. We're trying to figure out if the function exists. This is a similar kind of thing. Huge, huge, huge number. Same number of zeros as the one above. I'm not counting them, though. That kind of thing. So you notice it gets bigger and bigger and bigger. And you could plug in more of them, and it gets bigger and bigger. You could also take a look at the graph. I went ahead and graphed it. Do you see how it constantly is going up as it approaches 0 from the left and constantly going up as it approaches 0 from the right? Okay, so we have that going on. And so it gets bigger and bigger and bigger, and the graph is going to look like whoop, whoop, all the way up, okay, going there. So if you notice, it's not approaching a single value. From the left of 0, it's going to infinity. From the right of 0, it's going up to infinity. Okay, so the limit doesn't actually exist because it's approaching infinity. Okay, I say doesn't exist. It doesn't exist like at a specific value. It goes to infinity, and you'll see that as we go through more of these problems. One more. The limit as sine of 1 over x. We're going to see if it exists. And you could do an XY chart. And this is a great one to do an XY chart, but you've got to be good at your unit circle. Some of you need to practice a little bit on that. It's kind of evident in some of your homework assignments that you're not familiar with that. You need to know your unit circle. But you can plug in values in your unit circle and work on this. Consider 1 over x like a reciprocal. So whatever number I plug it in the bottom, I could just flip it. Okay, if it's a fraction, do it like that, and so it'll be easier for sine. So I'm going to plug in, I'll just show you an example, 2 over pi, because when I plug that in, I'm going to have sine of 1 over 2 over pi. When you divide by a fraction, it's the same as flipping that fraction. And sine of pi over 2 is 1. And so I would intentionally be picking values that would give me things like that, so that sine of pi is 0. Sine of 3 pi over 2, so think of it backwards, is going to be -1, and so forth. And you're going to pick these values, and it doesn't matter how far you go. It's going to keep alternating like that. The word for that is oscillate. And so this graph is really cool looking. It looks like this. Okay, if you look, and if you were to zoom in and zoom in and zoom in, maybe, cut out. It's going to look like coming here, here, oscillating, lots up and down, and then it kind of goes like this. Okay, and so it's real an interesting graph there, but the more you zoom in, the more squiggly it looks. It's not approaching a single value. It is constantly bouncing between 1, 0, -1, constantly going through that. And so since it's oscillating, it's not approaching a single value. It's approaching 3 different values all the time and never stopping. So this limit does not exist either. So there's some examples of that. You'll see some of these things show back up, and with some of the knowledge, we'll be able to find more values for them. But at this point right now, we will say the limit does not exist. All right, that is it for now, and you'll have a homework assignment with this too. This homework assignment I won't have due Friday, since you're just now doing notes on Thursday. They'll be due the following Friday. So you only have one assignment due this Friday. I do expect you to watch your notes by the end of Friday, though. You don't have to have the homework assignment done.